Hi again. We reached to the point that we wanted to apply dimensional analysis to this problem. And we noticed that there is something interesting with respect to the wall velocity u in this problem. If we think about the governing equation, the initial condition, and the boundary conditions, we see that they all have one interesting property. They're all linear with respect to u. In other words, if I have a solution for a given u, for example, 1 meter per second, and I call that solution 1. And if somebody asks me what would be the solution of this problem if I increase that wall velocity from 1 meter per second to 10 meter per second, I can easily give 10 times solution 1, and that would be my new solution. Because the governing equation, as you can see here, is linear. The initial condition is linear, and the boundary conditions are also linear with respect to u. The fact that the entire problem has this linearity with u, mathematically is easy to show that we can take the ratio of u, bring it out. So Vx over u cannot be a function of u anymore because it's a linear relationship between Vx and u. So it can only be a function of y, the y dimension, or the component of the y-axis, time, and the kinematic viscosity in u. Now, if we use our knowledge of Buckingham pi theorem, here we have 4 parameters, 1 and 3 here. And we have indeed only 2 important dimensions in this problem. We only have length and time. There is no mass. And if we use Buckingham pi theorem, we can find 2. So we have n equal to 4 and 2 important dimensions, k equal to 2. N minus k will be 4 minus 2. So we'll have 2 pi groups. Pi 1 would be the ratio that we have already formed, Vx divided by wall velocity u. And pi 2 would be a combination of these 3 that becomes a dimensionless ratio, becomes a y divided by a square root of nu times t. And this pi 2 is indeed what we call eta. So this is what we have done in similarity solution. The idea is this is our similarity parameter eta, and this is our similarity function, which we call it f of eta. So if you think about it, by defining this eta, we kind of took care of the variation of delta with time. If the delta is really evolving with time, if I make my y-axis dimensionless with delta at each instant of time, all these different solutions at different times will collapse to a universal shape or universal curve. That can be done mathematically by defining this similarity parameter, which takes the y and divided over this combination, which is square root of nu t. Which, in other words, implicitly is suggesting to us that indeed this y over square root of nu t or eta is suggesting to us that delta probably should scale as a square root of nu t. Now, for mathematical reasons and for making algebra simpler, we added a factor of 2, just because some of the coefficients cancel out if we add the parameter 2 there. And we said that, okay, eta is indeed defined as y divided by 2 square root of nu t. And similarly, f of eta is defined as Vx, which can vary as a function of y and time, t, divided by the wall velocity, which is u. Very soon, we notified ourselves that this is suggesting that delta of t is indeed scaling as a square root of nu times t. In other words, the length scale for diffusion of momentum inside our domain is increasing with time in a square root manner with a coefficient that is set by kinematic viscosity, or in some other way you can call this is the coefficient of diffusivity for momentum. Because as the wall moves and momentum starts to diffuse inside our domain, delta really is the length scale of this domain of diffusion as it's increasing with time. And very much like any other diffusion problem, whether you have diffusion of heat or mass or any other diffusion problem that you have seen in different fields of transport phenomena, it actually goes with a square root of time with a coefficient of diffusivity, which here is nu, that captures the diffusivity of momentum. Now, we did this, and we saw that actually mathematically this trick of defining a similarity parameter can help us to simplify the equation. And we found that the simplified equation in terms of f and eta turned out to be an ordinary differential equation, d2 of f d eta 2, the second derivative of f with respect to eta, plus 2 eta times df over d eta is equal to 0. So we found that the partial differential equation that we had now turns out to an ordinary differential equation. And somehow magically we notice something interesting happening at the same time. So let me actually, this is the final, I would say, similarity equation that we found. Like any other equation, this is a second order differential equation. We need certain boundary conditions. And since it's order 2, we actually only need 2 boundary conditions. But one may say we started with 3, so how come we ended up here and now we only have 2? Let's see what's going to happen to these 3 when we write them in the language of eta and f of eta. So the first initial condition becomes transferred to when time is equal to 0, eta goes to infinity, and f of eta, which is vx over u at infinity based on the first initial condition, should become equal to 0. So that's how our initial condition transforms to the language of similarity parameter and similarity function. The first boundary condition, which is the velocity of the wall as we start the impulse of the velocity to the wall for times larger than 0, should be equal to the constant u. And in the language of eta, that means when y equal to 0, that means eta equal to 0. And f of eta, which is vx divided by u, will become equal to 1. So f of 0 should be equal to 1. The other condition, which is velocity very far from the wall, should stay 0 at times larger than 0, because diffusion of momentum, no matter how long you wait, will not reach the infinite point that is infinitely away from the wall. And that tells us again y equal to infinity corresponds to a value of eta that is equal to infinity. And velocity there being 0 means that f of eta is 0. We see something interesting. We see that one of our conditions, the initial condition that we had here, collapses on the boundary condition that we had for y equal to infinity. And from this, we only get 2 that comes out. F of eta equal to 0 is 1, and f of eta equal to infinity is equal to 0. So the interesting thing is, the similarity parameter that we defined, it has combined 2 parameters, the length scale y and the time, which is t. So since we have the y variable and t time variable combined together in this manner, that we made eta with them, you can clearly see that when you have y equal to infinity or time equal to 0, they both give you eta equal to infinity. So in simple ways, the solution really is, if you'd like to think about it, was a surface. So you had the solution Vx, which is varying both with y and time. So if you had 2 axes, time and y here, Vx was really a surface on top. But by this collapse of y over time, we made it into one curve. And inevitably, this collapse into parameter eta will also lead to a collapse of 2 of the boundary conditions and initial conditions on top of each other. They collapse into only one condition, which is f of eta equal to infinity, which go to 0 for both of them. This is usually the sign, or the, I would say, the very good this is very good to identify when you are doing similarity solutions, because when you reach this point and you see that 2 of the conditions collapse on 1, it means that your definition of similarity parameter and the algebra that you have done until you get the equation, similarity equation, everything has been probably done in the right manner. So this is a good sign to see. We continued in our lectures to find the solution for this. We found that the equation that actually satisfies this ordinary differential equation and also these 2 boundary condition is nothing other than f of eta being equal to 1 minus error function of eta. And we then use that to actually plot that on a curve. So if you like to plot it, we can have here on the x-axis we can have f of eta, which is defined as Vx divided by u. And on the y-axis, we can have eta, which is defined as y divided by 2 square root of nu t. And we said that if you actually look at the solution from eta equal to 0, f of eta is 1. Eta equal to infinity, so eta equal to 0, which is this point. So this is eta equal to 0. I will have a 1, so that's 1 point. F of eta is 1. And eta going to infinity, which is far away, eta is 0. So the solution, if you plot it, it will be something like this. So this is the f of eta, which is 1 minus error function of eta. Just keep in mind that this is not really f plotted versus eta. This is eta on the y-axis and f of eta on the x-axis. But the reason I did it this way is the simple fact that you can easily convert this into the idea of the velocity profile, because eta equal to 0 very much corresponds to the fluid elements that are very close to the wall. And as eta goes to infinity, that corresponds to fluid elements that are further and further above the wall. And you can clearly see that this mathematical function gives you the physical idea that fluid elements close to the wall have a velocity very much similar to the wall. When you go very, very far away from the wall, that velocity diminishes and it goes to 0. So those fluid elements have not yet felt the motion of the wall. The question that will come is how much will take for fluid elements to really feel that, and that's the scaling that how y is scaled with. So that is this fact that the diffusion of vorticity or momentum in this problem, delta of t, is increasing with time in this manner, scales as a square root of nu t. If you like to plot and compare this to the velocity before converting things to the similarity parameter, you can actually look at a plot of velocity Vx without normalizing it, Vx as a function of y and time. And here you can have the y-axis here. So what you will see very fast is you will have a family of solutions. So we plot them with different colors. So let's do that together. We will start from an early time solution, which will be, so this is my u. The very first solution will be only few points and then you go up. So that's at an early time. At a slightly later time, you get this solution, which is the green. At a slightly later time, you get something that goes like magenta. And the basic idea here is we are really doing nothing other than, this is again Vx as a function of time and y. So this is how time is increasing. The blue curve is the early time, so you can call this T1. The green one is T2, the magenta one is T3. So as you start the motion, only few fluid elements here get dragged because of the viscous diffusion of momentum. At a later time, more fluid elements get dragged, that's the green curve. And at a later time, more and more fluid elements get dragged because of the friction and diffusion of momentum. You never really manage to give the velocity equal to u to every fluid elements, because no matter how much you weight, still diffusion has not completely filled your domain entirely. And that's because of the fact that the domain is infinite in size as you go to the higher and higher values of y. In reality, in real problems, we really don't have infinite domains. Our scale in the lab or real application usually has a finite length scale. And this solution is valid until the diffusion of momentum slowly reaches that finite upper limit of y. And that's the place then that the diffusion of momentum will probably saturate, and then you start to have a rigid body kind of motion in the entire tank. So the entire fluid elements and everything will probably feel this velocity and they will move with that. Or for example, in Couette case, when we saw that there's a wall here, if the wall is not moving and is stationary, when this momentum reaches there, the steady state solution will form, which will be just a linear profile that goes from u to 0 in a finite gap. So the whole concept of similarity solution, similarity parameter, and how it's actually useful in problems that there is no obvious length or time scale that emerges from the geometry of the problem, is something useful that you have seen in different lectures and recitations. I really encourage you to review it one more time, but to keep in mind the fact that momentum can also diffuse in a domain, and the diffusion of momentum usually gives this kind of a scaling, that the length scale of that diffusion is growing with time in this manner, which is going as a square root of time with the coefficient which is set by the diffusivity of momentum, which is also called kinematic viscosity, is a very important and useful concept that we will use extensively, especially in module 3 when we reach the topic of boundary layer. I stop here and we continue the rest of this review in the next video.